Okay. Multivariable functions. What's a multivariable function? It's a function which has more than a single variable. So f of xy equals to, say, x squared plus y squared. That's a multivariable function. Here's another example. You could have 3 variables as input, f, x, y, z, and you just have like x times y plus 5z, something like this. Now for this first case, what type of function is this? It takes how many numbers? 2 numbers, 2 real numbers, so you write it as R2. How many numbers does it give you back? No, 1. After you calculate x squared plus y squared, that's a single number, a single real variable. Okay? It's a single real value. So it gives you back a single number. Okay, so for example, what's f of 1, 2? There's 1 squared plus 2 squared, which is 5. So 5 is a single number, right? I fed in two real numbers, 1 and 2, and came back, it gave me a single number, 5. So I feed in 2, I get back 1. How about this one? What kind of function is this one? You feed how many numbers? 3, and it gives you back 1 single value. These functions are called multivariable functions. Now compare this with vector valued functions. What kind of functions are vector valued? You feed in a single number and it gives you a vector, which is more than a number, right? So t squared, 3t. Something like this. That's an example of a vector valued function. In this case, what does it do? You feed in one single number, and what does it give you back? R3, right? 3 numbers. Sometimes if it's a vector valued function in 2 dimensions, it'll give you R2. Okay? So it's like the multivariable function is like the opposite of the vector value.
They want all the doors.
Now you might ask, I guess the next natural question to ask at this point is, well then, are there functions which goes from R3 to R3? Okay. Is there any function that goes to R3 to R3? Or R2 to R2? And the answer is yes. There are functions where you feed in 2 real values and you get a vector, something comma something. Okay. Those are called vector fields, and it's much more complicated than what we're doing. So towards the end of this course, we'll be talking about vector fields. But right now, these are some easy cases when you have more than one variable involved, either at the output or at the input. I mean, this course is called multivariable calculus for that reason, right? How do you deal with a function when you have more than one variable? That's why it's called multivariable calculus. Now, the first thing that you want to learn about multivariable function is how do you graph them? So let's think about the graph of this function. How do we graph this function? Well, if you recall, if I had a function f of x in the single variable case, the graph of this function was simply writing the equation by coming up with a new variable y, set it y equals to that function, and then you go to the 2-dimensional plane and you plot all the points that satisfy this equation, and you ended up with some graph. Right? That's what graph of a function meant. Right? Therefore, for this case, when you talk about the graph of a 2-variable function, you need to come up with the 3rd variable, which we will call obviously a z, and we want to draw the graph of z equals to fxy. That's what I mean by the graph of a function when it's two variables. Okay? And you have z equal to, in our special case, is z equal to x squared plus y squared. Now, because this has x, y, and z, the graph belongs to 3 dimensions. Okay. And if you recall, if it was z equal to x plus y simply, what did you get? What kind of object in 3-dimensional space was it? Huh? If it was simply z equal to x plus y. Is it a line? Question, z equals to x plus y. What's the graph of this? Is this a line? No, what is it? It's a plane, right? So it's actually, it's a plane whose normal vector is 1, 1, negative 1. It's a vector, it's a plane which is perpendicular to the vector 1, 1, negative 1. All right, passing through the origin, right? And so imagine what's going to happen if you had square and square. Well, it's going to kind of warp this plane because these make it nonlinear. It'll make things bent. And therefore, what you expect is it's some kind of a surface. Right? So you're trying to think about a surface given by this single equation. Okay? So here are some differences. In one variable case, you had to say y equals to fx. In the 2-variable case, you had to say z equals to x comma y. And in the 1-variable case, the graph was in 2D. Here, the graph is in 3D. In the 1-variable case, the graph is some kind of curve. Here, the graph is some kind of surface. Now, it becomes mind-boggling if you think about what's the graph of a 3-variable function. In that case, you have to say w is equal to fx, y, z. And that's going to be 4-dimensional. And it's impossible to imagine what that would be, right? And the graph would be some 3-dimensional object in 4-dimensional space. Okay? It quickly becomes really, really hard. We'll never touch on this one. Okay? All right, so here we have z equals to x squared plus y squared. Now, the tools for figuring out the graph of a 2-variable function is, one is the trace. It's like the intercepts in the single variable case. So when you drew graphs in pre-calculus, often important information for drawing the graph was your x-intercept and y-intercept, right? Here, the important information is what kind of intercepts does it have with the xy plane, yz plane, and zx plane. And those are called traces. Okay? Xy trace, yz trace, zx trace. And another thing is, it's called the level curves. Not only you want to do the intersection with these planes, you also want to take different levels, and you want to think about the cross sections with different levels. So for different z value, you want to look at the graph. So those will be the tools that we use to picture the graph. Okay. So let's first talk about the the traces. First, xy trace. Now remember, how do you find the y-intercept in 1-variable case? If you're given y equals to f of x, how do you find the y-intercept? Set what? Y is 0. That's how you find the x-intercept. To find the y-intercept, you get set x as 0. Okay? So that's how you find the intercepts here. It's the same deal. XY plane is described as what equation? What equation gives you the XY plane? It's a collection of all the points that have height 0, right? What equation is that? Z equal to 0. Z is the height, so if you set z equal to 0, then you get the xy plane. So to get the xy trace, what you need to do is you set z as 0. Now, let's see what we get. If you set z as 0, you get 0 equal to x squared plus y squared. What is that? X squared plus y squared equal to number is usually a circle, right? In our case, what's the radius of this circle? 0. The radius is 0. So here's the xy plane. And the intercept it has with the xy plane is a single dot. That's all it has. Okay. Now what about the YZ plane, YZ trace? You set what as 0? X as 0, right? And in that case, if you set x as 0, you get z equals to y squared, which is, well, this is like y equals to x squared, only that instead of x you have y, instead of y you have z. Okay? So z equal to y squared could be read as y equals to x squared. What's the graph of y equals x squared? Y equals to x squared. What's the graph of this? Y equals to x squared. Parabola, right? So you end up with a parabola. And then xz trace. That would mean y equal to 0. And then if you set y as 0, then you end up with z equals to x squared. Then again, it's a parabola. X. So here's how you think about it. You have x, y, and z. And down here, the only intercept is just a single point at the origin. If you cut it in the yz direction, you end up with this parabola. If you cut it in the x direction, you end up with another parabola this way, okay? Now, if that is not enough for you to figure out the graph, the next thing that you want to do is to do a level curve. Well, a level curve is to set the value of z to something. So let's talk about z equal to 1 level curve. Z equal to 1 level curve would mean that 1 is equals to f of x comma y, which means 1 is equal to x squared plus y squared. What is that? What's the graph of that? It's a circle of radius 1, right? That's the graph of z equals to 1 level curve. So here's my crappy attempt at drawing the situation. This is the x, that's the y, and z is the height. For the xy plane, it just meets the origin. And if you look at the xz trace, it's a parabola this way. And then if you go to yz trace, it's a parabola going this way. And at level 1, what do you have? If you cut it at level 1, you get this circle. So it's a circle. Now, you could try to get more circles, more level curves. So if you have z equals to 2, 3, 4, it's going to go up and up, right? But each time you have x squared plus y squared equal to number, so it'll always become a circle with some varying radius. And because it has to pass through these, you can kind of see that it's a graph that looks like that. So what kind of surface is this? It's like a bowl, right? That's what it is. Or you can also say it's a volume of it's object of revolution. You take the parabola and you rotate it around, and you get this thing. Okay. Now there's a name for this thing. Because it's made of a parabola, you use parabol. And for surfaces, you put the word oid. Oid means it's a surface. So it's a surface coming from a parabola. Okay? Because it's a volume, it's an object of revolution from a parabola, you call this a paraboloid. And of course, there are other surfaces, like if you take the ellipse and you make the object of revolution, it's called ellipsoid. If you take the hyperbola and make a object of revolution, you get hyperboloid. So there are other surfaces. That's how you use xy trace, the traces, and the level curves.